Hello everyone, welcome to this video. In this video we are going to look at a formal definition of a group, right? So let's begin with this task here. So first of all, in order to define what is a group is basically consists of two things. One is a set, another one is a binary operation. So when we take these two things into account together, then that together with few conditions form a group. Now let's see each of these things in detail and recall what we already know about all these things, right? So first of all, let's review our knowledge of sets. So what are sets? They are well-defined collection of distinct objects. For example, we already know about various standard sets that are there. First is the set of natural numbers, right? It consists of all the numbers starting from 1, 2, 3 and so on. Next is the set of whole numbers, where actually it is a set of natural number with just a 0 added to it. So it is a bigger set than that of the set of natural numbers. So we have a set of natural numbers here, then we add a 0 to it, so it becomes the set of whole numbers, right? Next, if we add all the negative numbers also to this one, that is -1, -2, -3 and so on, to the set of whole numbers, then we have the set of integers, which we denote by the symbol z, right? So if we add -1, -2, -3 and so on, so what do we have here? This set would form the set of integers, right? Now if to these integers we add the decimal numbers also, the numbers which are in this form, p by q form, where both p and q, they are integers and q is exactly not equal to 0, then this is the set of rational numbers, right? Now if in this rational number, if we add a set of irrational numbers, that means the numbers which cannot be written in this form, p by q form, right? For example, the square root of 5, the square root of 2, pi and the exponential number e, all of them, they are irrational numbers. So if you also add irrational numbers, now irrational numbers, they do not contain any one of these, so they are simply a disjoint set. So that is the set of irrational number. Now if you add all of them together and form a newer set, that set is the set of real numbers, right? This is the set of real numbers, and here it contains both the rational numbers as well as all the irrational numbers. So basically this real set contain all the sets which are present before this one, right? And then we have the set of complex number, where we have the number iota, which is the square root of -1, right? So we have all the numbers x and y, right, which are taken from real numbers, which are represented in this way, x plus iota y. So together they form this set, which is the set of complex numbers. So this is our number system, and basically this is the standard sets that we already know, which occur mathematically, right? So with this knowledge of sets here, we may define the next definition of binary operation. So let me denote any binary operation by the symbol star, right? For this symbol star, what this binary operation does, it takes two numbers. So bi means 2, nari means numbers. So it takes two numbers from say S is the given set. From that particular set, it takes two numbers, one is here, one is here, and then apply that whatever is the operation here, right, onto it, so that it give you finally one answer. So an operator that works on two numbers to give us only one number. So let me give you various examples of this binary operation. Suppose our set is the set of real numbers. Then in that case, our operation that we have defined is multiplication. Now we have to check whether on this set, the set of multiplication, that forms a binary operation or not. So in order to check the binary operation, what we do, we take two elements from the set of real numbers and we apply the operation of multiplication onto both the elements there. Then we need to check whether it gives us a single number which is also a member of S or not. So this is what is our task. Suppose we consider any two numbers from S, then A star B, that would be A cross B in this case, multiplication. And when you multiply any two real numbers, you are again going to get a real number, right? Why? Because that is the fundamental property of real numbers that you already know. So therefore in this case it is a binary operation. Let's move on to the next example. In the next example, suppose our set is the set of natural numbers and the operation that we define is that of subtraction. Now we have to check whether this is a binary operation or not. So this is not a binary operation. How this is so? Suppose because in this case the property of closure does not hold. So that means if you take any two natural numbers and then you perform this subtraction, suppose we took 2 and 3. So when you subtract 3 from 2, you will get -1. Now -1 should also be a member of the given set n, but that is not so. -1 is not a natural number. Therefore this is not a binary operation, right? So let's move on to our next example. In the next example, the set that is given to us is a set of natural number again, and the operation in this case is defined as when you take two elements a and b and apply this operation, then what you do actually, you take a to the power b, right? The first element to the power of the second element. So this is the operation. Now we have to check whether this operation, this is a binary operation on the given set or not. So just pause the video and do it by yourself. So I'm waiting for your answer. Is it a binary operation or not? Okay, let me continue. So what we do here in order to check that it is a binary operation or not, we basically check that a to the power b belongs to the set of natural numbers or not when we take both a and b from the set of natural numbers. So the answer is it is a binary operation. Why? Because when you take two natural numbers, say 2 to the power 3, what you get is 8, which is again a natural number, and this is true for all the numbers which are member of the natural numbers. So therefore this is a binary operation. But now if I change my set, if I change, instead of natural number, if I take the set of integers here and apply this operation that a star b is equal to a to the power b, then it is not a binary operation. Why this is so? Because when you take the power of two integers, they are not always integers. For an example, if I take the first element as 5 and the second element as -1, both 5 and -1, they are integers. So according to the operation that we have here, if the answer would be 5 to the power -1, and 5 to the power -1 is 1 by 5, and 1 by 5 is clearly not an integer. So therefore this is not a binary operation, right? So you are clear with sets, you are clear with the binary operations. So what we do here is, by using sets which are equipped with one or more binary operations, in certain case we use only one operation, and in certain case we use two binary operations. So using this thing, what we do, we create abstract structures, right? And which few of them I have listed here. First one is group, where we have one set and one binary operation. Another one that we'll study later on is rings, where you have one set and two binary operations, two different or same binary operations. And third one is field, where you have one set and again two binary operations. It could be same or it could be different, right? So these are few of the abstract structures. Then you also have modules, you have Lie algebras and many more things like that. So here, what is our goal? Our goal is to study this much portion, groups, right? So in order to understand what are groups, let's define the formal definition of group. So the formal definition says, if we consider G as a set together with a binary operation, usually in most of the cases we take it to be multiplication, but it could be any binary operation. So let's use this star symbol in order to generalize the concepts and result. So if G is a set together with a binary operation, so that means if it is a binary operation, we are inputting two numbers a and b from the set G, right? And it would give us back one single number, and that one single number is also a member of G. This is one thing. This is the property of closure, which basically is already available to us by the way of binary operation, right? So we say this G is a group under this operation if the following properties hold. So basically this closure property is already contained in the word binary operation. So whenever you are checking for certain groups, you should also check this closure property, right? So because you should also ensure that the given operation, is it a binary operation or not. In addition to that, we have following conditions which make the given set together with the binary operation as a group. So the first property is that of associativity. So what does it do? We wanted to check that the given operation, the given binary operation, is it associative or not. So basically we take 3 elements from the group in this case, right, from the set, and we check that when we apply A star B first and then perform it star with C, whatever is the answer, we do it with C, or we perform B star C and then perform star with A, in that case whether they both are equal to each other or not. So this is the property of associativity. The next one is the property of identity. Here in this case we say that there exists an element which we denote by E, which we name by E. This element is basically known as the identity, right? So there should exist an element E in the set G such that when you perform AE you get EA, and what is that? That is just A, the element itself. So basically this element E does not do anything on the element A. So that when you apply the same operation onto it, or basically I should write here instead of this AE here, we should write A star E, or we should write E star A, because this is the binary operation and this is the binary operation for all A in G instead of these, right? So this is the property of identity. And next is the property of inverse, where we say that for each element A in G, so for every element we are talking this thing, for every element here we say there should exist an element B in G. There would be some other element, let's call that element as B, which we call as inverse of A, such that A star B should be equal to E, and whenever we do B star A, that is also should be equal to E, right? So this thing should be there. If that is so, A is the inverse of B and B is the inverse of A, and this should hold for every element which is a member of the given set G. If all these three properties hold together along with the closure property which is given by the binary operation that is given to you, then the given set forms a group under the given binary operation, right? So in addition to this, we also have a property of abelian and non-abelian group. So if we have the commutativity, that means A star B is equal to B star A for every element, then we have the commutativity in the group and we call that group as an abelian group, right? And whenever for few elements this commutativity A star B is not equal to B star A, then we call that group as a non-abelian group, right? So I hope you understood the definition of group. In the next videos we will be looking at various examples of group. Well, that is it for this video. Thank you for watching.